This is going to be the introductory level presentation today, and we're going to talk about soil colors and what those soil colors mean to us. First of all, I'd like to start out by just introducing myself again to those that maybe have not been to a webinar before, one of mine before. I'm an extension specialist at Virginia Tech, and my specialty is soil science, primarily in soil formation and classification and soil survey, but I also like to relate soil properties to land management and land use decisions. So a lot of my presentations talk about things like sand, silt, clay, colors, parent materials, drainage class, and things like that, but they can be applied to soil health, soil quality, production, soil tilth, and management of soil problems and things like that. We have other extension specialists that are experts at soil nutrient management and crop production and so on. The department quite literally has a dozen extension specialists that like to work with ag agents and share information. So this is one way that I thought we would try to connect. In just a minute, I'm going to go to a slide that will talk a little bit more about how you can give me feedback about the type of training that you would like to receive. And I think that's a good way for us to communicate as well. So I'm going to start just real quick by letting you know who I am. And my name, again, Dr. John Galbraith, and I enjoy especially going to the field and teaching people about soils on site. So we thought that we would use this webinar series as a way to present basic information as a refresher, and then follow that up with some on-site training. And again, at the end of this PowerPoint, there will be a slide that shows you a link where you can send me your requests for on-site training. We have two trainings set up right now, one in the Southeast District and one in the Central District. And later on, we'll do the Northern District and then the Southwest District. And that way, I'll get a chance, hopefully, to meet agents and naturalists in person. And I guess the first two trainings are in-service training, so it'll be for agents. But at other times, I'll be attending events of master naturalists and master gardeners and other groups around the state. So my background, I come from South Texas, spent a lot of time in the western United States, and then basically started moving after that, and have circled around from Montana all the way up to New Hampshire, Minnesota, Florida, Virginia, Alaska, and lots of places. So I've had a chance to be around. Well, let's get started on the webinar now that we've had a chance for people to join in. All right, so first, I just told you who I am. I'd like, again, to encourage you to use the chat to ask questions either at the break, and at the end, I have a break for questions in the middle. We've asked you to turn off your mic, and that looks like everybody has done so. I appreciate that. And then I'm just wondering if a few people, we have plenty of time today, can a few people just using the chat just tell us who you are? Tell us a little bit about yourself. My name is Bob Smith, and I work in the Loudon office, and I'm a A&R specialist or something simple like that. Would anybody like to introduce themselves? Well, I could pick on Trent Jones and ask him to tell us a little bit about himself. I know a lot about him, I think. He was a student here just a few years ago. All right. Mark Sumner is logged in, and he's with Cal's Information Technology, and he's the mastermind behind this webinar. I wouldn't have been able to present this without him. Hi, Nikki. And she's an A&R agent from Greensville County. Good to have you here. Debbie Dillion is a Hort agent serving Culpeper, Madison, and Orange. That's great. Hi, Debbie. And Tom Bowles and with Prince William, and turf and school gardens. That's an interesting combination. Great. Master Naturalist, Bob, good to have you here. And Elizabeth Hodson, and a mosquito control biologist. Interesting. And there are so many vector-borne diseases that we have to worry about. Well, thank you guys for chiming in and letting me know who you are. Just as a reminder, you don't need to hook up your video or your microphone, really just a headset or speaker so you can hear. And we will be recording this session, but any chat that you put up there will be anonymous after this session. I will selectively pick some of the better questions, and we'll post those to the Virginia Cooperative Education webpage, but I won't reveal the name of the person. It'll just be the question and then the answer. So feel free to ask any question, and no question is a bad question. We will be posting these again to the Cooperative Extension webpage, and that'll be listed under the Natural Resources menu. And once you get on that menu, then you should go down through the soil information choice and then click on that, and you'll see a couple of tabs that talk about past webinars, questions from the webinars, and then another tab we're going to ask them to add that says lists the future webinars. All right, well, let's get into soil color then. And this is almost an outline of the talk today. So essentially we'll be talking about color. We'll start with topsoil, because this is what the layer that most people see first and they're most interested in, because that's where they plant seeds, that's where they walk on, that's what they're most affected by, is the topsoil. Well, the plants may be more affected by the subsoil, but humans tend to focus on the topsoil. And we'll talk about the colors that are revealed when bedrock decomposes, because we do get a whole variety of colors left behind when that happens. And I have the other colors broken down into reduced colors and oxidized colors. And what those two terms mean is really whether the individual elements are in a reduced state or an oxidized state. And reduced state means that that the valence of the element is lowered because it has gained electrons. So why is that important? Why am I even mentioning those, and why did I even break them into those categories? Well, the reason is because when reduction occurs to an element, it becomes soluble, and it also loses most of its pigmentation because it goes from a crystalline substance to a soluble substance, and therefore it becomes part of the soil water, or soil solution is another way to put that. Oxidized elements, however, tend to form crystals, and once oxidized, those crystals then capture sunlight, light, and they then have a color to them. So typically, reduced elements are colorless, and oxidized elements have color. It's not always true, but that's a pretty good generalization. So let's go ahead and move on with that. Okay, so with the topsoil colors, we have organic carbon type makes a difference. Products from burning make a difference. And organic carbon content makes a difference. By the way, can everybody see the screen? Is anyone having a problem seeing the screen? If you do, let me know. All right. Okay. Hopefully that is working better. But under organic carbon types, we have the types that form under grasslands and the types that form under forests. And under products from burning, we have burning that occurs in grasslands, burning that occurs in forests, and then we have burning that occurs in factories. And then under organic carbon content, or in other words, the total percent carbon, then we can relate the soil colors to the percent carbon. So let's take a look at some pictures now. So under organic carbon type, we have several different types, but let's look at grassland soils here. And there's two pictures of grassland soils. The one on the left is semi-arid grassland. And so there's not much moisture and not much carbon being produced. Now the types, the one on the right, has a lot of organic carbon being produced and a lot of carbon being stored by that soil. So this soil on the right would be an example of an area that is humid and gets lots of moisture. The one on the left would be an area that is dry and gets very little moisture. And you can see the difference in the color of the topsoil because of that. Now, in general, in grasslands, we get what are called humic acids, and of course we get humus. Humus actually occurs in all soils, but in grasslands, the humic acids are really, really common. Okay. So again, the relationship between moisture and color and content is very evident in this picture. In forested areas, we get a dominance of fulvic acids. And the difference between a fulvic acid and a humic acid, as far as color goes, is that humic acids are very dark when they're moist, but they stay dark when they dry out. Fulvic acids, on the other hand, are very dark when they're moist, but they turn very light in color when they dry out. So it's a difference in how dark that soil appears when it's dry. So here's an example of a forest soil. It's not as dark to begin with, and as this dries out, it will get even lighter in color. One thing to note in this picture is right in the center is a big piece of charcoal, and there are several pieces of charcoal in the picture. And that leads us into burning and products from burning. So we have grassland soils, and they contain black biochar, and this is from burning. And when you get thick amounts of grass on the soil surface, you know that it's like hay. When you cut hay and you windrow it, but before you, then you have to turn it. And the reason you turn it is so that the bottom can dry out. Otherwise, moisture gets trapped underneath and the hay begins to rot. Well, the same thing happens in a grassland. If you have a high production of grass, and then that grass falls over during the winter, and the next spring a fire starts, well, that grass is probably not going to burn completely to the ground because it will still have moisture trapped underneath it. And that's a special thing, because if you get incomplete burning or burning with low oxygen, you end up with black charcoal. And we think of charcoal as actually being burned up pieces of wood. We also get biochar, which is essentially just a very, very fine version of charcoal. It's charcoal from grass, if you want to think about it that way. But again, it's incompletely burned, and that's why it's black. We all know that if you throw wood in a fireplace, the first thing it does is it drives off all the gases and the moisture. And the second thing is it turns black. That's charcoal. Then the third stage of burning is when it goes from charcoal to ashes. So incomplete burning in absence of oxygen leaves us a black biochar or black charcoal, depending on what kind of material we started with. Well, many soils also contain soot, and soot is black, and this is what escapes the smokestacks if they don't have proper equipment on them. And in many countries, there is no regulation on what is released from smokestacks, or it's not enforced. And so when black soot comes out of a chimney of any kind, and whether that be a diesel truck, a brick factory, a coal burning plant, whatever it is, that black soot, if it's a very hot fire, the black soot will go into the upper atmosphere and stay there for 2 weeks. And it circles the globe, and then it falls wherever the wind takes it. And so primarily there are certain parts of the earth where that gets concentrated, and the black soot falls even more so than other places. And one area where that happens a lot would be areas that get monsoon rainfall. Okay, and at lower levels, in other words, the soot that doesn't get high into the atmosphere, well, that falls very near the source of the soot. And again, it is a black pigment that actually does change the color of the soil. Now, we don't notice it much, but if you have ice or a snowfall that lasts for a long period of time, and if you live near a factory, you will notice a little black film of black dust that accumulates on top of the snow. And of course, that makes it melt faster. And that's a real problem if you have a glacier or snowpack in the mountains. Okay, organic carbon content and how that's related to color. Well, we have these correlations here. So we have moist colors of value 3 or more, chroma 3 or less, and these are colors that come out of a soil color book. So if we have these colors or darker colors out of a soil book, it means that there's at least 0.6% organic carbon. And in these pictures down below, let's look at the relationship. Here we have a very light colored soil, topsoil, and it has a very high value. And the carbon is low. So the higher the value, the lower the carbon. Also, the chroma is 2 in this soil. In this soil, to the right, we have a value of 2. So much lower chroma, much higher carbon. More than 10 times, 20 times as much carbon. So just a few changes in color that get darker indicates that you're increasing the amount of carbon in the soil. And these soils have a low chroma, and that means they have even more carbon. So the closer you get to the left bottom corner of a color book, the more organic carbon you're going to have. And this is an example of how native people added biochar or incompletely burned plant products, and they added that to their soil, and they were able to change the color from the soil on the left to the color of the soil on the right. Okay, well, let's take just a minute and see if there are any questions about the first part of today's talk. You know, we primarily covered the relationship between organic carbon type and organic carbon content and the color. Okay, and so here's a question about why add biochar to soil. Well, there's numerous benefits to adding biochar to soil. The native people discovered that in their burn piles, they added manure, they added food waste, they added bones and other things before they burned the piles, but they oftentimes covered the piles of wood with dirt and soil. I said dirt. Oh my gosh. I guess I should have said soil. They covered it with soil, and then that caused incomplete burning. And then, of course, they noticed that in these burn piles that they had extremely fertile plant growth. And I think that would be my guess as to how they first discovered the benefits. And then they realized that this pile of debris could become a source of fertilizer for their fields. And so they started spreading it onto the fields. And then now we have, the result is that even 500 years later, 500 to 1,500 years later, the soils are still fertile. But in general, what biochar does is it increases the water holding capacity, it increases the fertility, it increases the pH of the soil, and it increases the ability of the soil to hold on to other nutrients that you add. Are there any other questions about the difference between the type of carbon in, say, grasslands versus forests? It was pretty much a landmark observation when soil science first started. They primarily separated soils into two types, grassland soils and forested soils. And the reason was because they noticed how black the grassland soils were and how the forest soils appeared to have lots of carbon, but then after they were cleared, they quickly lost carbon. And the grassland soils just had a higher reserve of carbon and fertility, and so they were able to farm those for much longer periods of time without adding nutrients or fertilizers. And back during the early days of soil science, there were no really good commercial sources of fertilizer like there are now. Okay, well, if there aren't any other questions, then we'll go ahead and move on. So the organic carbon content and the colors that we just mentioned, those were primarily for mineral soils. So in other words, those made primarily out of sand, silt, and clay. Now let's talk about soils that are primarily made out of organic matter, decomposed organic matter. And so let's just use as an example here, an example of pine needles rotting away and then being incorporated into a sandy soil. So we start with pine needles. Some of your friends or yourself may have a place down near Virginia Beach. Got a lot of pine trees in your yard. You pile up the pine needles underneath the trees every year. After a few months, they start to turn a reddish brown color, like in the center photo. And a few months after that, they actually develop a very dark color right at the base. Well, you can see in the picture to the right, you can see the reddish areas are actually accumulations of rotted pine needles, and that's been incorporated into the soil and enriched this sandy soil. So another example of a place where we can see degree of decomposition is in a marsh soil. So here we see a marsh soil where somebody has grabbed a large shovelful and pulled it apart, and they can see the roots from the marsh grasses, and also you can see a reddish brown color from the organic material. And here this color is actually inherited from the plant parts. And again, now in a marsh, you know, we get incomplete decomposition. So this red is not from iron. This is from the original color of the plant parts. Off to the right, we can see the dark color at the surface, and that color is due to very high and complete decomposition of the organic materials, and this would be called sapric material, or muck. It's another word for it. And this is the color of the material we would find underneath pine needles or oak leaves, in the forest. And this is very highly decomposed. And this is the same as humus. This is turned all the way into humus. Deeper in the soil, in this marsh soil, you can see plant parts that have not completely decomposed, and that's because this soil stays too wet for complete decomposition. Okay, here's some bedrock colors, and we can actually see the pattern of the bedrock in both of these pictures. The original color banding in this bedrock is evident, and we have associations now. Now that we've left the organic matter and we're dealing with mineral materials, we can talk more about the effect of iron, because iron oxide is extremely dominant as far as a color agent in soil. So we get yellows and reds colors in decomposing bedrock, and those yellows and reds are often due to iron oxides. Oranges, other colors. The light colored bands in here are primarily due to quartz. And then there are many different kinds of rocks, such as limestone, that begin as gray colored. And as they begin to weather, they release iron, and that iron forms iron oxides. It oxidizes and turns red. So that was earlier we talked about the difference between reduced and oxidized minerals. And here's an example on this picture to the right. The reduced colors, the center of the rock is reduced and it is gray. The outside part of the rock is oxidized. It's been exposed to oxygen, and the iron has migrated to the edge of the rock and it's turned red because it's now crystalline and no longer soluble. Here we see some saprolite, and this is rotten bedrock. If it wasn't rotten bedrock, they would not have been able to cut such a nice smooth surface here. In other words, this material looks like rock, but it's no longer cemented. But these bands of white in here, rather than being quartz, most of these are actually kaolinite. So we get this in the Piedmont, and I've seen it most often over near the fall line. If you get a deep road cut or a fresh road cut, you'll notice some white bands, and they look like white wax. And if you pick them up, they feel quite waxy, and that's actually the mineral kaolinite. Then we have mica flakes, and this is not true mica. It's not muscovite. It's a weathered version of mica, but it breaks off into tiny, tiny specks in the soil. This is a piece of rock, but in the soil, these individual specks will appear in the soil. And we've all seen the Piedmont and Blue Ridge soils that contain a lot of mica, and it's shiny, and it's really pretty. Sometimes it's silver like this, sometimes it is gold like this. All right, what about gray colors? Well, here we have on the left is actually a very, very close-up of silt particles. Some of them are dark, but most of them are gray. There's a few that are white, but most of these are gray in color, and that's pretty much the background color of small soil particles, especially silt and clay. Most sand is colorless as well, but it really depends on the minerals. A few of these sand grains you can see are almost perfectly clear, and then there's a few that look like they're bright white. But look at the other colors in here. Here's a red one, here's orange, here's green, here's gray. There are all kinds of colors in here, pink, and it just depends on which mineral has been broken down into a sand-sized fragment. The sand is made up of various minerals, and each has a different color. So most sand is either white or clear when it's uncoated. That means there's nothing coating the grain. And most sand is also quartz, and Again, quartz is either white or clear for the most part, unless it has a coating. The picture to the left shows quartz particles that are coated, and they're coated with a very, very light reddish color, very light tinge, and that's actually iron oxides. And that's why the grains appear orange to you, even though if we were to wash these coatings off, it would look like the sand grains in the center picture. And then we've all been to the beach in Virginia or anywhere on the Atlantic coast, and you can see the sorting of the black mineral grains. And these are heavy minerals, and these are things like ilmenite and magnetite, or actually they're magnetic minerals. To do something for fun is take a magnet to the beach sometime, loosen up this material. It often forms a crust. Loosen it up and then take a magnet and pass it over the loose sand, and I think you'll see some of those particles will become attached to your magnet. But those are commercially very valuable. Also, there's rutile and zircon, and those contain minerals that are very, very valuable, and so they're being mined actually in places near Old Hickory and other parts of the coastal plain. Other reduced elements, well, we have reduced iron and sulfur compounds, and those can be anywhere from gray to blue to almost green. And so the picture in the center is reduced iron oxides, and it's dominantly gray in color. There's a little bit of oxidized iron in here, and that's the red color. The picture in the center is a special type of iron, and it's called glauconite, but essentially it's green, and the soil is green when it is reduced. On the right, we have soil or sediment. Actually, this is more like sediment than a soil, because you can tell it hasn't even been dry long enough for vegetation to form. But in this sediment, you can see how black this is. Well, it does have a fair amount of organic carbon, but really what it has more so of is sulfides. And sulfides are just reduced sulfur. And so the reduced sulfur is a very black color. And these are called monosulfides. Well, here's some soils that start to look like upland soils. I guess I started out with the exceptions, and now I'm ending up with the most common properties. On the left, you can see a pattern of reds and grays and yellows and oranges in the soil. I guess there's some browns in there. Maybe that's a better description than yellows. We can also see that some of the pebbles are stained with orange color, and some are stained with red color. So here in the center is one stained with orange. Here is one stained with red. And right down the center are some pebbles that are not stained at all. Well, this is the reduced part of the soil where the iron is soluble. So it moves out of this part of the soil. The red part of the soil is where the soil is crystalline or oxidized, and that's where it forms compounds that they reflect the red part of the color spectrum. And so you can see the red. And typically, these are either the difference between the orangish brown color and the red. They're typically different types of iron and different amounts of iron, different concentrations. So the more iron, the brighter red it gets, but also different types of iron as well. And again, when we see a big gray area, typically that's where iron has been removed. But again, interesting thing is look how it affects the pebbles. Pebbles in a reduced zone are white. The pebbles in an area where there's some concentration of iron are orange. And pebbles where there's a big concentration of iron are coated with red. On the right is the picture that my soil judger took yesterday. And we went to a soil pit to look, and there's two things that we see here. Here's where we see the yellows and the orange colors, and also some red from oxidized iron, we see the gray from reduced iron, but we also see these black patterns. And what those actually are is areas where manganese has concentrated. So these are typically soils that have a drainage problem. Both of these soils have a drainage problem. And this is color pattern that we see is a mixture of grays and reds. That is an indicator to us as to where the water table is in the soil. And in this particular soil, the water table, all of this part of the soil on the right are underneath the water table, and the same thing with the soil on the left. At least during some part of the year, the water table rises through this zone and also through this zone. Now, the picture on the right has a lot of manganese, and most of the time, manganese will be the dominant mineral. However, there's always some iron oxide in there. It's never pure manganese. There's always some iron in there. And when the concentration of either the manganese or the iron gets high enough, these actually become cemented. And when we cut through this with a shovel, you can see that it's smeared in a few places. And the reason it's smeared is because we were cutting through these cemented pieces of black soil. Now, this is not charcoal. This is a mineral, and you can tell that because when you crack it open and hold it to the light, it reflects the sunlight and sparkles, and charcoal won't do that. When you hold charcoal to the sunlight, you can actually see the structure of the original plant parts. Well, here's some more oxidized elements. Earlier, we showed you the monosulfides that were black. Those were reduced, but when the sulfides do oxidize, they precipitate as a yellow compound. And of course, we all think of sulfur as being yellow, so it should be no surprise that a yellow compound that contains sulfur would be yellow as well. And so this material is used to be reduced. It's now exposed to oxygen, and it's forming brand new minerals called sulfates. And one of the most common sulfate is called jarosite. Okay, and I have a question about the green picture, the green soil that we saw just a moment ago. I'm going to go ahead and finish this slide, and then I'm going to take the two questions. So the middle slide here is plinthite. So our second bullet is plinthite. And then plinthite looks like a brick in the soil. In fact, it acts like a brick in the soil. Once it dries out, it is cemented. So this is an iron cemented mass. Now, there are lots of these colors, patterns in soils that are not cemented, but millions of years ago, about 1.8 million years ago, North America was in a more tropical zone. And at that time, this material formed, and it is called plinthite. It is cemented iron oxide and primarily hematite, formed in tropical regions, but it's now found in the soils of the Piedmont, I'm sorry, not the Piedmont, the upper coastal plain right next to the fall line. Right near the fall line is where we find this. And it's left over from a previous climate. But again, you have to cut it open with a knife or break it open with a hammer. And then on the right, we see what's called, these are humic concentrations in the soil. So we can see the source of the humus is this very, very light surface. But once the humus goes into the subsoil, it combines with aluminum, and it forms a very, very dark layer. And this looks like a lot of the soils that we might see in the lower coastal plain, especially along the Blackwater River. There are many terrace soils, so you get very, very white, uncoated sand, and underneath that we get very, very dark sands that are coated with organic matter, humus, as a matter of fact. Well, I'm going to go back just a little bit now and try to answer a question. This is about glauconite, and the question was, doesn't glauconite fade from green to gray really quickly when exposed to air? Actually, it stays, true glauconite stays green, and when it's exposed to air for long periods of time, it releases bright red iron concentrations because this is an iron-bearing mineral, and it was deposited underneath the ocean. So geologically, once it gets exposed to the air, it starts to release the iron, and it's released as an oxidized form because it's exposed to oxygen near the surface. So this particular clod or aggregate must have come from pretty deep in the soil, or it would have a lot more of these red colors spread throughout. Now, there are some wetland soils that do change colors when you pull them out. So let's go to this soil on the right. If I was to pull some of the soil from deep down underneath the water table and then set it out on the surface and let it oxidize for a while, it would change color. And in fact, that's why you can see this reddish crust on the surface of this soil. It's the only part of the soil that's been exposed to oxygen for very long. And it does change color. But typically, true glauconite will stay green and then turn to red. And other types of iron compounds besides glauconite may change colors from blues and greens into grays and then eventually into reds given time. So a very, very good question. And then this is I guess the finishing touch here, and that is just to note that almost all of these colors in these three soils are due to either an addition or accumulation of organic matter of various types, some that are high, some that are very, very low, like in the center picture, and then the other colors are due to uncoated sand grains, which we see in the picture to the left, or various stages of either reduced iron, where the gray colors are, or oxidized iron, where we see the red colors. The picture in the center is very typical of soils found in the Piedmont. And those soils are oxidized throughout, and they have lots of red color because they contain lots of iron compounds, and they're all oxidized, and so that indicates a good drainage. The soil on the left would have restricted drainage in the subsoil, and that's indicated by these patterns of reds and grays. And the soil on the right probably is pretty well drained as well, but it looks like it has some bedrock properties toward the bottom, so it's just not a very, very deep soil. So the colors of the soil are influenced by the elements that are inside the soil, particularly organic carbon and iron. Well, while I'm announcing these links here, if anybody else has any questions, please feel free to add those to the chat. If you have requests for webinars or training, you can go to this link and you can add your input and let me know which topics are important to you. There's a place to vote, and then there's a place where you can fill in your own information and you can request training. Also, I have a Twitter page at VAsoilguy. I guess that's supposed to be a capital A, so that might be important. VA should be capitalized here, just like it is down here. And on Facebook, I have a Facebook page that's related to the Cooperative Extension. And then on the Cooperative Extension webpage, this is the main link here. Okay, does anybody have any questions? Somebody is looking for the link right now on the VCE webpage, and I can tell you that we're within a few days of having that completed and posted. I've actually seen a draft copy of it, and I knew that it might not quite be up yet, but they are working very, very hard to finish it up. And when they do, then we'll have the past webinars will be posted as YouTube videos. So it'll be very, very easy for you to store those, share them, post them, save them, whatever you would like to do. And so that's our goal. But again, we're just at the very finishing stages of getting that done. Like I said, I've seen the draft copy and it looks really good. But we did have a few requests, so you might say we asked for a few more changes to it, and that's why it's not quite up yet. But it will be just almost immediately. Okay, well, I had a nice comment about the talk, and I hope you enjoyed the talk. I know that was quite a bit. There's more to soil color than we realize, and one area I did not expand on as much as I could have is the relationship between soil colors and drainage class, but that'll actually be its own webinar later on. And so again, we'll keep that as a separate topic and look forward to seeing you again. I will post this, but I'd like to wish everybody a good week, and we'll have a webinar again tomorrow with a little bit more intensity to it, a little more detail, but not on this subject. It'll be talking about landforms in Virginia. So thank you for checking on, and I hope everyone has a great day, and we will see you at the next webinar. Thank you.